right. What's up, Ace? Yeah, no problem. Just do what you got to do. I just realized my comments on the side are like way off to the edge. I'll have to look into that. All right. Let me get this set up. I think my camera's a little weird too. Let me fix this real quick. Apologies. I usually do this before the stream starts, but I got a little ahead of myself here. Let's do that and then make the focus a little better. Oh, hold on. I'll allow that. I don't know why the auto mod caught your comment there. Yep. You got to get it all done. I hate deadlines. I'm so glad to be out of school. All right. Where's that thing? There. That looks a little better. Okay. Get my manager set up. Okay, there we go. Good to go. All right, let's get started back into this. Somehow build a lightsaber. Okay. So last time I pulled up a lot of the ideas that we came up with last time, and I still want to do all of them, but we have to think through this some because this is gonna be pretty difficult. And while we came up with some ideas for things, I didn't really think that they were all like the best option we could come up with. So I'm trying to figure out exactly what I can do to make this easier. And primarily, the one I want to really solve and do some research into tonight is the power issue. I want this to be really bright, and in order to do that, I have to push a lot of power. So when we did the Millennium Falcon and we lit that up with the NeoPixels, I bought a 10 amp power supply, AC/DC converter, which is a lot. That's like 5 times as much as any of those fast cell phone chargers. So it's like 5 of those in one. And that is an insane amount of power to try and pull out of a battery. You know, there's a reason your phone is designed to use low power and everything, is just because, yeah, you can't push that much. So I got to figure out how this is done. And we found some options last time, but we found an Adafruit board that did a step up, but even it couldn't push that much. So I don't know what to do. Like, I want it to be rechargeable, but I also need to be able to push a lot of power, and that means this is going to be kind of hard. So what did we look at last time? I think I pulled this up in one of our assemblies. Where's the assembly one? There it is. The boost board. Most of these lithium ions are 3.7 volts. Okay, yep, this thing here. There's quite a lot to this too, to like manage the power and everything. I think we could, this circuit doesn't look that complicated. Maybe we could just do our own circuit if I knew but not with these controllers. I can't solder these by hand. Everything else I could. I could get 0805 parts, which are fairly big surface mount parts, and do that, but I cannot do these little chips by hand. I can't solder them onto a board. What even is that? TPS 61090. Is this even the right one? Because it says, okay, so I'm looking here. This is a TI part. Synchronous boost converter with 2 amp switch. Switch data sheet. Let's see what this offers. They only offer us in this VQFN package, which is really hard to work with. I wish I had a soldering, I wish I had an oven. That would make this way easier. But I need a hot air rework station too. The circuit is not too bad. I mean, there's a lot of parts, yes, but I think we could work on it. Henry's simplified application schematic. 96% efficient boost converter with a 500 milliamp output current from 1.8 volts input. Input voltage is 1.8 to 5.5. Adjustable output voltage up to 5.5. Fixed output voltage options. Is that what these are? Are these different output voltage options? The maximum peak current in the boost switch is limited to a value of 2,500 milliamps. That's a lot, actually. What happens if you put 2 of these on a board? There's got to be a maximum and minimum ratings here somewhere. I don't think we can use this part, but maybe we can find something similar. I mean, I'm getting more and more into the realm of we just need to do a giant custom circuit board for this. Which I'm all for, by the way. I think that would be really cool to build. And for you all to watch me build. Just see how a circuit board is actually populated and how all the parts and everything are put on it. It'll be another exercise in me trying not to burn myself over and over again. Oh, hold on. I got it. Here, I'm going to adjust one of these bounties too, because I know that this is going to be a hard thing, so I want to offer something for it. Reminder, if anybody completes one of these bounties, you get the payout for it. 5 Dogecoin right now is like $2.50 too. This is going to be really technical. Find a 3-axis emitter. I'm probably butchering the spacing on this. Yep. IC in an SOIC or through hole package. If you don't know what that means, don't worry about it. Just Google 3-axis accelerometer SOIC or something. Actually, I'll Google that right now, see what happens. SOIC 16 accelerometers. Ooh, this is interesting. Wow, they're expensive. Like $25 for one. It's not even a stocked item in some cases. All right. Yeah, good luck on that one. If anybody claims that bounty, they'll have earned it. All right, so this. Power. Input voltage range. Switch current limit at 5 volts. You should, okay, so 2 amps should be our kind of assumed. I want 4. Shoot. How much is 60 neopixels? 0.06. That's 3.6. Yep, okay. I want 4 amps capable. Voltage range, feedback voltage, slider frequency. I think that'll be okay. We'll have another regulator that'll clean that up some. We can throw a big capacitor on it too to help. We're going to need a really big capacitor with a heatsink. This is going to be hard to solder without hot air. Let's see. Oh, also, if anybody was paying attention to the, not that I would expect anyone to, but the stream archive channel, I had to make one of the videos private. I actually got a copyright claim, which kind of sucked. So, I don't know how that happened, but the music got recorded onto the video. I don't have permission yet to put the music that I pay for on that channel. All right, so maximum output current versus input voltage. Oh, okay. This graph makes a little more sense because I was surprised that I could put out so much current. So maximum output current is over here. Input voltage is here. We're going to be at 3.7. Oh, wow. So we can really only get like 1.8 amps out of it. Do we use multiple of these? I mean, that would be insane, right? This thing's going to get warm. Oh, it's different per chip. If we get the 61009 one, then it's higher. What's the difference here? Oh, is it a lower voltage though? We need the 61092. That's the 5 volt out. Hold on. It seems kind of weird the way this is worded. Maximum output current versus input voltage. Okay, yeah, so it's this one right here. The 61091 is much better, but it puts out a lower voltage, which makes sense that I could put out a higher current. Okay. Yeah, I'm definitely going to accidentally set something on fire doing this. I like that they list very specific types of components, but yeah. Okay, so the typical application makes sense. R3, R4, what do those need to be? Doesn't say, does it? Does it say up here in the? I know that there was another schematic. I thought, yeah, here. Okay, here it gives a equation for what resistor values you need to put there. All right, so this part seems pretty straightforward. So now I need to know what this other item is, which is like not very well presented. Let's see. Just be aware the charge rate is 1000 milliamps max, and there's some inefficiency during the boosting stage to make sure that the USB adapter you're using to charge with is high quality to supply 2 amps of thick power. Lower quality ones are not active due to voltage drop in the wire. This is especially true if you're actually drawing 1000 amps out of it. It maxes out at 1.8 amps. Well, that's good to know. So 1.8. Okay, we're close. I need to know what this other chip is, but it's like I can't read it, the part number on it. Also, does anyone know, can you connect lithium-ion batteries in parallel? Is that a bad thing? Like, assuming they're the same charge, right? Does it just make one battery, like effectively one battery with a bigger capacity? Oh, here's a schematic. This will be good. This will tell us what that other chip is. It uses the 61090. Oh, that's weird. Two amp, 4 amp boost. This is really hard to read, by the way. I apologize. It's weird that they use the 61090 because I didn't think that could go up high enough unless they're boosting into another one. Because the 61090 V out is 2.5 volts, but it needs to be 5, right? What is this other chip? This is going to be just a night of me looking up and Googling things, searching things. MCP 73671, is that what that is? $73871. Is that what they're using? Hold on. Are they boosting one into another? MCP 3871. This is a microchip part. USB AC battery charger with power path management. Let me see a data sheet. So this is the thing that controls the charging. Oh, excuse me. One amp fully integrated linear solution. Here, I'll just pull this up so y'all can see. Okay, interesting. Show me a data sheet. Standalone system load sharing, lithium ion, lithium polymer battery charge management controller. So it's expecting 5 volts in, which it will then drop down and... okay, I think this is making more sense. Okay, yes, so the TPS 1090 is used to power this, and then that is the controller coming in to control charging the battery, and those two things are wired together. Technically, yes. I take that. So you're that's what I'm thinking. I'm thinking if we wire them in parallel. If you wire them in parallel, I think that just makes effectively a big battery. The series part I'm not so sure about because we want to make this rechargeable, and most stuff is designed to recharge things up to 3.7 volts. I like what you're thinking. I really do. Like it. It would be cool if we could do that. I just don't know if we can charge it. I might just go off this schematic, though. That's at least what I'm thinking about doing at this point. Use this schematic as a guideline. And then, where is it? Where is the schematic? Did I miss it? That's the layout. It was here. It was just here. Nope. It's gonna get hot. This is gonna be great when we make a lightsaber that heats up so much you can't touch it. Here it is. I don't know why I couldn't find that. So if I go off this, I might be able to figure out a way to, or at least I should be able to make my own circuit, basically. All right, let's just, for a sanity check, each cell hangs around 4-ish volts. Yes. Is your RC car, how is that recharged? Because we could definitely wire a bunch up in series to make it work. This is going to be a huge lightsaber when we're done, too. I can't wait. So that's actually not a bad option, too. It's a lot easier to step down. If we could do 2 cells, then I could regulate down to 5 volts. Battery attracts a specific charger. Not entirely sure how it works. Okay. What is this called? Battery management. Let's see, battery charger. Let's just go with that. Maybe that is the answer. Maybe we just say screw it on the step-up converter and we just try and go with a couple batteries in series. All right, here we go. Power management controllers in DigiKey. There are 3,500 of them. Ooh, some through-hole stuff too. I like these. Easier to solder. Okay. What do we need here? We need lithium ions. Ion and ion polymer. That's most of them, thankfully. In stock, and well, let's not worry about that part yet. Battery pack voltage. So it should be 3.7 times 2, right? So 7.2, is that an option? It's not. Okay. Is there like an application or something? Yeah, most of these things are tiny too. This is the only annoying part. This could work. Electronics, lithium ion polymer, $1.03. What does this do? Constant, programmable, battery pack voltage, 8.2 volts. Voltage supply max is 15 volts. Interesting. Will ship in approximately 10 days by Rochester Electronics. Interesting. Okay. What is this? So ideal for a single 4.1 or 4.2 volt or dual cell 8.2 volt or 8.4 volt lithium ion. Requires a small number of external components. SOIC or TSSOP. We want the SOIC because that is the only thing that I can really like solder myself. Did you get it? Yeah, I don't accept links in chat. Sorry about that. You might be able to whisper it to me though. Although I don't know if I can receive it. I've not used whispers before. Oh, SOIC is not available for 8.2 volts. It is for 8.4. Okay. Oh, I thought that was all the external components. I was like, a small number of external components. Jeez. Okay, here it is. Yeah, diode resistor there. Debounce cap there. This is the battery pack. Temperature sensor. VCC. Okay. I think we're getting closer. I think this is interesting. I need to see about the batteries again, though. Rechargeable batteries. Okay. Is this 8.4 an option? Here it is. $9 Obsolete or $13. This is a nickel metal hydride. That's not going to work. We need these two. And to clear this. Yeah, no, and I totally, like, anticipate that. My problem is I'm not even trying to focus on having enough capacity. I'm just trying to focus on pushing enough power instantaneously. You need a lot of current to drive it. And so that's the problem we're dealing with here. You're absolutely right. The battery, at best, I'm guessing an hour if we really go for it. But even then, I don't think so. I'm thinking probably around 30 minutes with everything we're going to have on there. See, the problem is most of these come in 3.7 volts. What are our options now we've selected lithium ion? Here's 7.2. I like that a lot. $27 battery. 3.25 amp hours. That's cool. There's 0 in stock. But seriously, is this just 2 of them connected together? Because if it is, then we can do that. Capacity, weight, charge voltage, standard current, 0.2 C. Max charging current, 0.5 C, 0.2 C. C is capacity, right? So 0.2 is like 600 milliamps. Ugh. That's not as much as I was hoping for. We need a few of these. I really don't want to get into the world of like, this is a ridiculous problem. And that's probably the reason that NeoPixel lightsabers are not done very often is because of this. Let's try something else. Clear that. Capacity. I want to know... it won't give me a discharge. What's 12 amp hours look like? Is it just a big block battery? Yeah, this is like a laptop. What if you had to wear a backpack that had a battery in it? Wow, this is taking forever to load. I clicked on datasheet and it's giving me a Shopify link. Interesting. All right, we'll let that load while we look at something else. Nine millimeters by 168 millimeters by 135. Yeah, that's huge. I just want to see like, oh, well, really? It won't even tell me anything? All of that just to load this page. I wanted to see what its output, maintained output could be, but I guess not. Okay. All right, let's try this again. Lithium ion. So I guess the alternative is then we connect 2 of them together. 4.4 amp hours. That's great capacity. If we could, these are these Adafruit ones that we were already looking at. It's just 2 of them tied together in parallel, I think. So we could tie that in series. We just need a way to charge it, which would be 7.4 volts. Discharge rate 2.2 amps. How big is it? $4,400 milliamp hour. Okay. By the way, thank you for the ideas and everything. It's been helpful, jogging my memory and just kind of helping me out here. Yeah, it's literally 2 batteries connected here. 37.5 millimeters. It's not quite 2 inches. I don't care much about the length, but the width I do. It's 37.5 millimeters. I don't have a reference here. That's like 1.5 inches though. If we use a really thick handled lightsaber, we might be able to fit that in there. Alright, hold on. Let's look at let's look at a single cell one. Voltage rated. Let's just go with this 3.7, and then see what we can find. I think capacity, we're going to need something sizable. I prefer 2 amp hours or bigger. We'll see what this gets us. We're going to figure this out. We're going to figure out a way to do this. 2.5 amp hours. That's awesome. 7 volts. This isn't too expensive. What is this? I didn't even look if there was any in stock. 0 in stock. So it won't tell me what the maximum like constant discharge is, because that's what I need. All right, let's go in stock, because we need to pick from a reasonable list. Too big. Those 6 amp hours is pretty great. If we could use 2 of those. It's only 2 inches wide. That's still too big though. That doesn't have measurements. It's huge though. 6,600 milliamp hours. This looks exactly the same as this one. Yeah, PK cell, PK cell. It's Adafruit selling PK cells. They're made by the same company. I think this is the single. Yeah, the 2,200 milliamp hour. Okay. I think this is the one we were looking at. It definitely was. Okay. What is the max current? maximum continuous discharging current is 2C, 4,400 milliamp hours. That's incredible. I take that you might be on something. If we use this battery that we've already picked before, how expensive is it? $10. Okay. If we can wire 2 of them up in series, then we should be fine to or produce 7.4 volts, which will be enough to power everything. The other thing we have to consider is it holds 2,200 milliamp hours. So if you discharge at 4,400, you're discharging twice as fast. If you discharge at 2,200, then 2,200 milliamp hours lasts exactly 1 hour. If you discharge at 4,400, then it lasts exactly half an hour. Kind of. For whatever reason, the way batteries work, they tend to have lower capacity if you discharge really fast. So I think this could work. We just got to figure out a way to charge it. And we got to wire 2 of them up in series. And then figure out a way to charge it. And then, yeah, we should be able to discharge incredibly fast. It will get so hot, but we could do it. So charging cutoff voltage is 4.2, so we need an 8.4, I think. Battery charger, battery chemistry, battery pack voltage. So do we say 8.4? Is that a common one? There are 121 left. I bet you they're tiny, though. We got to find one that's easy to use, easy to solder. So no Media, Texas Instruments, switcher, or sorry, this one. Yep, $2.13, 36.51 immediate. Number of cells, 2. 8.4 volts. 8 SOIC. Oh, shoot. You know the other problem with charging is we gotta boost the voltage from the... we gotta boost the voltage coming into the charger as well. Maybe this thing does that. All right, let's look at a data sheet. If this chip works, I'm gonna be so happy. We'll have our solution in place. Then we'll just need a voltage to step down, actually, which is a great problem to have. 0.4 volt lithium ion battery packs. So this is the one I think we were looking at before. We need to double check that the SO... I think it is the one we were looking at before. That's really funny. So, okay, so we need the SOIC package. So we need to make sure that's available in 8.4. SOIC, it is. It's this part number right here. And then what does its input voltage have to be? That's the question we need to ask. Because I want to be able to charge it through a USB. Supply voltage, anything up to 18 volts. I mean, that's the max that it can handle, but what does it need to charge to 8.4? .5 to 15, so 5 volts. Right? Threshold, upper temperature threshold. Interesting. I have a good feeling about this, but we need to confirm. This is our circuit. It wants a temperature sensor. Okay, here's the operational thing. Oh, man. Occasion information. Using P-channel MOSFET. And it gives you the one it wants you to use. That's got LEDs here too. All right, cool. Looking good there. All right, sorry, just checking some things. Low current side sensing. Oh, I think I'm getting this. This is the controller. You still need to bring in enough voltage to charge. Okay, so we still need to step up. Okay, this is going to be tricky to use. I really want to try it though. So this is the basic one. Which one are we using? BQ2057WSN. All right, does that matter here? U2057. Okay, so it doesn't matter the package. So we have VCC. And then we take, this is the control line. We have a small resistor in there to limit the current so it doesn't just short. And this is the battery sensor, the voltage sensor. The temperature sensor, which I don't know that we have, so we might have to figure out how to do that. Or figure out some way to hold it that it doesn't matter. That sounds like a bad idea, actually. These batteries don't have a thermistor in them, do they? Thermistor is a temperature sensor, I think. Yeah, it's just two wires. It's just power in, power out. Yep. Well, interesting. Okay, so I just realized here it says 1.1 amps on the discharge rate, but in the thing I was reading, it says it can do 4,400 milliamp hour, 4,400 milliamps. Let me just scan through this real quick. Over discharge. They put it in an oven to test it. That's good, because otherwise we're going to pull a Samsung and blow the batteries up. So the capacity is going to be this at standard discharge. If we go a lot faster, I bet the capacity is lower. However, it doesn't give us a graph to show us what the typical capacity is going to be for a high discharge rate. I think we're just going to have to be careful. We might have to like design something in that if it doesn't work, that we could shoehorn a couple extra batteries in there to make it better. Okay. So that's that same data sheet, so we don't need that twice. All right, I'm going to go ahead and pull up the assembly and just make sure we have this battery, right? I don't feel good about this charging board, so that's what we're going to try and do differently. And we found a controller that I think I like. Which is this, the BQ2057. I can close that one. Now we need something to step up to this voltage. Let me find the pinout description here. All right, so CC is the charge control output, voltage sense input, station input, temperature sense input, supply voltage ground. Input for an external battery temperature monitoring. Connecting this input to VCC divided by 2 disables this feature. Okay, so you can disable it if the battery doesn't have it. You just have to connect it to whatever VCC is divided by 2. I guess that's like the ideal temperature, like the perfect temperature, so it would just ignore it. And it shows doing this exact thing here. Having a voltage divider between VCC and this. All right. 0.5 amp charger using P-channel MOSFET. What does this one up here? Low dropout, single or 2-cell lithium polymer charger. I think this is the circuit I'm going to use. Figure 1 shows the schematic charger using a PNP pass transistor. Oh, it's showing you how to use different transistors. Okay. So we could possibly change the circuit depending on if there's a dropout issue or something. All right, so what are the max and minimum? Come on. There's so much here. I love every part of this. This is all packaging and footprint stuff. We'll use this to design our circuit board. Where's the max and min characteristics? Here it is. Okay. Let me duplicate this and open it in the other screen so I can see the circuit and what I'm doing. That'll help me understand it a little better. Oh, I'm really excited. I think that you might have just hit the nail on the head here. Like how to do this. If nothing else, we're going to blow a battery up and it's going to look cool. It's not going to look cool. But you might have hit the money shot with that suggestion of doing the 2 batteries in series. All right, so VCC, as long as they're... No, what's going to happen is the handle's going to get really hot, and if it's made of plastic, it's just going to melt. And then we're going to ruin it. I want to make the handle out of metal if possible, but then it's just going to get really hot and burn your hand. I was looking up how much a block of like aluminum would be to mill it out of, and it was going to be like $400 for a big enough block to make 2 lightsabers. That's insane. Reg is output voltage. Where's that? All right, what's VCC like max? Supply voltage VCC up to 15 volts. And I think you have to supply at least whatever you're charging to. So we got to supply at least 8.4. Maybe even higher, though. I guarantee we do this wrong at least once. This is going to be so expensive. I'll figure that out eventually. I don't see a way where we can realistically build this whole thing without taking a long time and buying parts over a long period of time, but we'll see. So on that note, I do accept donations, and if you check the About page, I do accept donations in crypto as well. And you can type exclamation mark, I think donate in the chat, and it will tell you the different currencies that I accept. And then you can type exclamation mark like Bitcoin or something, and it will tell you the address. I think. If you want to fund me building this thing. Yep, there it is. I accept Bitcoin, Dogecoin, or SafeMoon, or the Streamlabs donation. If there's any other cryptos I should accept, let me know. I'll set up a wallet and add them. Okay. Yep, I think this works. I think we use this part, and this is how we do it. But we need to find a step up now. A boost to, and it needs to be able to supply at least, like, probably at least an amp. I think this circuit is designed for 500 milliamps. Can you go higher than that? It doesn't look like any issues there. It just come down to the transistor. Where is it? Here it is. I think our current's going to matter based on this resistor and this transistor here. Excuse me. All right, we spent an hour so far getting this far, but I really like the solution better. Just because it's going to be fun. We'll have to find all of these parts, but for now I'm just going to mark this particular one. Here, PCBA bomb. We've already, well, might have to come back to that speaker. Say PMIC, hold on, where is it at? Don't want that one. This one, and we want specifically the SOIC, the BQ2057WSNTR. Let me make sure that that is the 8.4 volt one, because that would be tragic if we grabbed the lower voltage one. BQ205CWSN. WSN. Yep, this is it. Okay. Excellent. So how's everyone's Thursday going? Here we go. All right, part number, manufacturer is this. And then get a DigiKey link. I might go through and try and get this stuff off Mouser later, because Mouser seems to be doing a better job shipping all this stuff. All right. So now we need a boost of some sort. Something to boost to 8.4 volts or higher. I guess you can go up to like 15, really. Voltage boost. DC-DC switching regulators. And I want to go from 5 volts to more than 5 volts. All right, in stock, active, 1,622 remaining. I feel like this part shouldn't be that hard, which is a good sign that it is actually going to be really hard. All right, basically anything higher than this should be fine. Ooh, 100 volts. Do you think we need to plan for that just in case if we're charging off of a 100 volt? Yeah, let's go with that. All right, and then we need the output voltage, and we need an SOIC package or a through-hole package. We'll worry about that in a second. Voltage output max. They have like inverters. Output minimum fixed. We need something high. Yeah, like 8.5 or up. All right, let's see where this puts us. I'm not optimistic, but we'll see. What is this? Voltage input max. Voltage output is 12. I like that. Here's an SOIC package. All right. What are our output options? If we get a little closer to the actual 8.4, we'll have a little bit of less like waste. This one's adjustable. That probably means it's expensive. It's not expensive. Is it hard to use? That'd be kind of a tough thing to solder by hand. SOT23. Yeah, I'm not doing one of those by hand. SOIC is the best we get. But there's a lot of through-hole components, which I really like. We're going to use one of those, actually, if at all possible. What is this on semiconductor one output? 12 volts? Yep. Oh, I didn't even think about the output current. Yeah, we need at least 500 milliamps. And I'd prefer more. Current output. 500 all the way to 7.42 Gs. All right. All right, so we're getting closer. Man, there's some cool stuff here. There's some expensive stuff here, too. I don't want to pay 12 bucks for a regulator. But I might have to. All right, so apparently those ones that stepped up really high are not like high current. Five amps, 3 amps, 5 amps. I think we need to go a little lower than that, actually. Because the max charge rate of those is usually like 0.5 C. So if it's 2200 milliamp hour, it's like 1.1 amps. So really like 2.2 is kind of the highest we can go. What is this little through hole one right here? That's 500 milliamps. You got to do the math too on that because 2.2, that takes like 4 hours to recharge. I dig it. If we go to like an amp, we can go a little faster. I think we shouldn't go faster than an amp. I think that's probably like not safe. But the output of this shouldn't affect that. It shouldn't matter what that resistor is and everything. I think if we just pick one, it'll be fine as long as it's decent. All right, let's go above 500. Let's get it to 1.2 at least. We'll go in this range here. Let's see what we got. How much this is going to cost us. I've almost at this point accepted the fact that since I'm not going to be able to afford to build it, I've just thrown cost out the window and decided, hey, let's just design the thing that is the coolest. You know? Like, let's just make it the thing we want it to be. And then maybe I can convince somebody to fund it. What is this Rochester one? That's an 8 SOIC. That's interesting. 1.5 amps, 12 volt output. I actually kind of like this one at the bottom here. It's cheap too. Okay. So I guess I gotta decide how much we really need. Oh, minimum quantity, 76. Oh, we don't want that. All right, we may not be able to get that one because the reason it's cheap is because you have to buy a bunch of them. We're gonna have to spend a little bit of money. Sorry, guys. All right, these analog devices incorporated ones look fairly decently priced. They're SOIC packages, and they can produce quite a lot. 1.2 amps. Well, they all pretty much cost the same. Let's get the 2 amp one. What is this one? Comes in a tube. You got to get at least one. 12 volt, 2 amp output. Voltage input 2 to 9. Puts out 12. 120 kilohertz. I like it. We're getting this one. On the condition that the input current is reasonable. Give me a sec. I want to know what the input needs to be, because I imagine you have to put in a higher amount of current to get a lower amount of current at a higher voltage, right? What's I in? Let's say input voltage, yada yada. Anything else is in microamps. I gotta figure out what the input voltage is here, because it could very easily, you have to be something that you have to like make really high. You're going to definitely need like a 2 amp phone charger to do this. But it doesn't say. The shutdown pin is too. There's going to be definitely some logic here. Oh, we're so close to having this solved. Current 12 volts. Also, just for the record, I am looking for some more music too, so we don't have to listen to the same thing over and over again. I like the music, but it's hard to find like stuff that I can play that I won't get dinged for, so. What are these different? 2-volt powered flash memory generator. 3.3 volt. Yeah. So we're gonna do this. We're gonna have to do this 5 volt to 12 volt circuit right here. 47 microfarads. Wow. Okay. I'm a little lost here. I'm trying to figure out. I just can't find an answer to my question, and there may not be one. Output voltage, output current. If the current goes up too high, the voltage starts dropping. If EN is 5 volts. Wait, I thought I could put out. I may not have picked the right thing here. Look at this. If VN is 5 volts, and it starts dropping out at 250 milliamps, I thought it was supposed to go way higher than that. Is switch current the input? That might explain something. I don't think that's right, though. All right, back. Output type. Current output. Yeah, so that should be okay. Interesting. I might have to pick something else, though. What is this one? Minimum startup voltage, 3 volt or 5 volt to 12 volt converters, rules, battery powered equipment. They don't do well at high current loads. Which apparently I didn't realize. So we might have to go for a more expensive chip here. All right, let's go for something ridiculous. 12 volt 3 amp. Let's go for this one. Let's see what this says. We seem to be gravitating towards a lot of TI parts. Texas Instruments. Because everything's bigger in Texas. Simple boost regulator for multiple output regulator. All right, how does this work? 3.35 volts, 12 volts, and adjustable. And we want just the 12 volts. What is the spacing on this? Oh, it's like, okay, hold on. We'll have to be careful what package we get this in. This is designed to stick like through hole into the board. That would be a little tough spacing wise. But it might work out well if we need a heat sink. I'd prefer to have one laying down on the board though. All right, let's see what our input voltage, anything there. Switch current is internally limited. Supply voltage, okay, so 5 volts. Output switch voltage, yada yada. Output switch current, less than 3 amps. Let's see. This will inevitably be a real expensive calculator. Yes, it will. That's pretty. You made me laugh. Dang it. Ah, I didn't mean. Crap. I don't know if you did that on purpose, but you did make me laugh. Congratulations, you claimed a bounty. 5 more Dogecoin on top of the 5 you already got for suggesting this project. Somebody else needs to get in on these bounties because this is getting ridiculous. I take that you need to send me a Dogecoin address. If you click receive in whatever wallet you have and copy that address, you can even just post it in the chat here because that's a public facing address. You know, the worst somebody could do is send you more coins. All right. So I need to see a graph for like input voltage versus current. Evidently what I was looking at last time, but didn't like. More typical applications. This might be, wait. What is this? This might not be what we need. It needs a transformer. No, I'm not doing that. I refuse. We're picking something else. I refuse to do that. 2586. Maybe we do go with this one that I was looking at earlier. Let's see what these maximum integrated chips do. What's the difference between these two? Stack up, boost, programmable. Ugh. Oh, one's the like crazy temperature range one. Yeah, let's get the cheaper one. Does this require an external transformer? No, just a bunch of capacitors and inductors, which makes a certain amount of sense. Yeah. Generates 100 milliamps or 125 milliamps. What? I thought it was supposed to generate 2 amps. Rules, portable instruments. Supply current 20 to 30 milliamps. Low input voltage. Gotcha. Maybe we go with this one. I told you that I was like, oh, this part should be easy, which is why it's going to be really hard. And it was hard. Oh, this is like an ideal footprint. I like it when they have these. Tells you how you should line up your circuit board for it to work. Okay. I don't know that this is going to cut it either. Why do they keep... So what does this mean? Output switch currents 2 amps, but then it says you can supply 100 or 125 milliamps. Like, I just don't understand that. It has a logic control. It changes it from 12 to 15. You can tie it, so... Does it give a... Wow, this has actually turned out to be way harder than I thought. Inverting section switch output. Oh, okay, you can... It's an inverted as well. Interesting. All right, maybe I can find something that's like... Nope, 2.0. What? Where is it? I can't even see where that is. It's treating most of the stuff as pictures, so... You know. Yep. That's the only thing. Wow, that's dumb. Okay, we got to find something. We're not using these ones that require transformers. This is going to bring me back to this one. All right, what was wrong with it? Let's see if we can figure it out. Can deliver 5 volts at 100 milliamps from a 3 volt input, 12 volts at 60 milliamps from a 5 volt input. For a 5 volt to 12 volt at 200 milliamp converter. Switch current is 1.2 amps. What does that mean? Because it doesn't seem to be lining up with the other stuff that I'm looking at. So I must not understand something. All right, what is let's here, have an electronic stack exchange. So to supply an output current of X amps, you need to be as a switch current limit. So unless your output power requires it. Okay, this is, okay, so to supply an output current of X amps, you need to V out divided by Vn times X plus I ripple divided by 2 is a switch current limit for Z. Okay, I'm getting closer. I can barely read this. If you want to simplify version, I'm looking at an example data sheet. The peak switch current in a boost converter is equal to the average input current plus half of the peak-to-peak ripple current. The math is hurting my brain. Average input current at 100%. Not even remotely adequate. I'm going to figure this out eventually, I promise. You know, I'm thinking through it. We might just have to make it so that it can't charge off the USB-C. Because I can get a high-powered, like, some sort of, like, high voltage, like, high current input to charge the batteries. But, yeah, it's just, this is complicated. To step up like that, that may honestly be easier. Yeah, I might actually do that. That might actually be a lot easier and a little bit safer, at least in terms of, like, less risk in the design. Because it's less components required, right? So let's look real quick. USB-C port. Because this is what I'm going to have to do. Connectors. USB Type-C. Let's see what we got here. If any are, I need something that's easy to mount is the problem. And sometimes that can be really hard to do. Yeah, so something like this, right, with all these little pins is not a very good option. But I don't know if there's anything better than that. I want something with a bunch of little like through hole things. Yep, this has it. Man, those are tiny. Oh, but there are other plates in the back. Dang it. Not what you want. All right, so that was closer, but not what you want. I want it to be through hole. I want it to be a receptacle as well. So let's start with that. All right, we want the whole thing to be through hole. Stuff. Is that an option? Through hole right angle. Let's see what this gives us. Yeah, I mean, this stuff looks pretty close, right? Oh, that's not right. I like that. All right, let's look at this one. I don't think I clicked on this one. Ah, it's still got pads. Maybe we can't do the USB-C. Just because there's too many pins. Yeah, because it's got some through-hole stuff and some pads, which would be really hard to solder by hand. All right, let's check a couple more just to be sure. And $4 for that one. I really don't want to order that if I can avoid it. Molex. That's a big company. This might work. Yeah, it looks like, okay. Yeah. It looks like it just has pins coming down. Yep, it does. Some are left out, which I think is fine. Okay, we get this one then. So that's what we're going to do. We're going to use a barrel jack, some sort of connector, and then a high-powered like charger, and then we'll just use the USB-C for like data. Okay. Here. Let me add this to our PCBA bomb. That way we can have it. So we got our charger, and we need our USB-C connector. How do you wrap in this? I don't know how to wrap an open office. Open office. Text. Right click. Format cells. Alignment. Oh, wrap text element. There it is. Okay. Can't believe I had to Google how to use OpenOffice. I picked the wrong description, actually. I want this one. Oh, this is a USB 2.0 as well. That explains a lot, actually. Why it was, why there were so few pins. Okay. Part number. This is for Molex. So they're going to have a random part number. Yep. And then a link. So I think that right there is our whole power solution kind of worked out. We have our charging thing, controller, and then we have our USB-C connector, and we're going to have our barrel jack. And then the USB-C is going to be kind of weird. I'm just thinking about it now. I'll have to look up how that's laid out, because we're going to have to connect to the Teensy's USB, which I don't think is on the board anywhere, like in the pins. So, right. That might involve splicing some wires and doing kind of a weird setup there. All right, I think that pretty much solves our power problem. Supposedly. So that's actually done. Our battery pack as well, I think, is good. I think we're done there. We got a lot more to go, though. Next one I want to look at is motion sensing. Because that was one I put the bounty up for and it hasn't been claimed, and I don't think it's going to be claimed. Accelerometer. We might have to use an evaluation board on this one. Which would be kind of annoying, but if we gotta, we gotta. All right, we want X, Y, and Z. This is interesting. How expensive is it? $179. Not as interesting. All right, in stock, active. Let's just make sure we're buying parts that we can keep sourcing. Oh, I'm getting a little tired. Is there anything SOIC? Oh, I saw one. What does this look like? It looks like $60. All right, maybe we ignore that one then. Service mount, flange mount, connector, chassis mount. How many are there left? 71? All right, let's just look through them all. Yep. See anything here that catches our eye? I mean, some of these are really cool. Like, yeah, these little mount things. They're just super expensive. Let's change the price on this. Other way. But apparently you can spend $2,800 on one of these. Getting expensive. Getting expensive. Yeah. Yep, really expensive. All right, so I think we are looking at like a breakout board type of situation, some sort of evaluation board. Did we come up with one in the assembly here? Acceleration sensor. Yep, this one right here. Found this in Mauser. Yep. This tiny little board. And I think we need to stick with it. How much is it? $5. All right, that's fine. The connectors are weird. But because of the size and everything, I think we stick with this, definitely. Oh, this one's even smaller. I kind of like this, actually. Well, I do like this one, though, having the 4 mounting points. All right, give me a schematic. I just want to see what this looks like. Oh, I also need to check if it's 5 volt or 3.3 volt compatible. Wiring diagrams. Yada, yada, yada. Here. As usual, really hard to read. So it's I2C, which we can use. It's just annoying. It does have headers, though. That's kind of cool. Maybe we could do some sort of like clip thing, but I don't think that's necessary. I think we just go through the mounting points on the board. It just means we have to manage the I2C. Okay. They have a code example? They do. So I wonder if it just keeps receiving for forever and you're just reading the values. Standard gravity for value and LSD acceleration. Oh, this is Python code. That's why this is weird. They have C code. That would have made a little bit more sense, probably. It looks like it's designed to be used with a Pi. That's what makes me worried that it's not 3.3 volts. That it's actually 5. Because aren't Raspberry Pis like 5 volts? Maybe not. Read over I2C. You can use it with either 3.3 or 5 volt systems. Oh, it's already got the level shifting logic in there. Oh, well, that's nifty. I just need to know what the... Let's see. Okay, so it would take a regular 3 to 5 volts. Okay, interesting. So it's got that part already. So that part's great. So I think this is a good solution. I think we can say our accelerometer is done. Yep, accelerometer board. So, okay. So we resolved that last time. Seeing we're good. Okay. I want to do LCD screen next. Mostly because I'm avoiding that speaker like the plague. I don't know why. All right, let's see what we can find. LCD OLED graphic. In stock, active. Now let's just start with the lowest cost because that'll probably be what we have to buy. You can get some that are dirt cheap too. Wow, I think we're going to spend like $10 or so at least. We need a really thin one. That's too big. How big is that? 0.96 inches. Wow, that's tiny. How do you control that? They've superimposed this picture on it as if it has a high pixel count. I don't think it does. Yeah, 160 by 80. That picture looks way better than 160 by 80. That's false marketing is what that is. I want to look at this though. It may be too small though. I'm thinking the screen is. I mean, it's cool that it's already mounted on a board and has like headers and stuff. So I think you can do, it's SPI, 4-wire. Okay. Yeah, it's already got these headers on. That would make it easy to mount. But, excuse me, I don't see this working well long term. It's just not very big is the problem, right? Like it's so tiny. Everything else about it looks fine. Yeah, I think we go for something else because it's just too small. I'm not a big fan of these ribbon cable ones, but I think I might have to go with it for this. Let's see. What kind of screen? Man, some of these would be really hard to work with. Like, look at that. Look how close those connectors are. That's kind of cool. All those pins. You just lay it on the board. What is this? 2.2 inch. Interesting. Backlight. That's kind of cool. How does this connect? 122 by 32 dots. I think it's a single color. This must be like a power and ground or something. And then you have, yeah, a bunch of through hole. This is not bad. $122 by, wait, no. 122 by 32, but like how big is it? 18mm by 60.2. It looks, okay, I like it. I like it a lot. It just doesn't look as good as some of the other ones. Did we pick out a screen last time? I think we did. Didn't mark it though, so. That's the display though. What similar one? Oh, that must be green. Yeah, we definitely want blue. Or black. Whatever that G is. Okay. Let's keep going. New Haven. I like New Haven stuff a lot, but it may not work well in this scenario. Though, it could just mount directly to the circuit board, which would be way easier for us. Ooh, I kind of like the red. How big is this? 36 by 12? It's pretty small. .32 controlled through SPI. Oh man, I kind of like this actually. See what the mounting looks like. I like New Haven stuff a lot. Like they make some good stuff for like these kind of projects. So it just oh wow, it extends out kind of far. I didn't realize that, but I guess that makes sense. It does extend out a lot farther than the screen is, so we have to work around that somehow. But I don't think it's actually that big. 24mm, so that's an inch. I think we can make that work. Because I'm kind of imagining this on the side of the lightsaber and like a slot cut and it like recessed back in a little bit. You know, to kind of be away from getting accidentally hit or something anyway. Okay. I kind of like this. It's SPI, right? I think so. Yeah, 4-wire SPI. Voltage, 3 volts, VDD, 6 volts, LC. 6 volts? Really? Or is that a max? You have to connect a bunch of capacitors in there. That's, you know, whatever. What are A and K? Oh, that's for the backlight. Anode, cathode. Okay. That's, yeah, whatever. We can wire in a circuit for that. And then VDD. This one right here. Power supply. Supply voltage for LCD and logic 3 volts. I like that a lot because it's a 3-volt system as well. What was it saying about 6 volts? Supply for LCD. VLCD has to be 6 volts. Contrast. What? Where is that? Does anyone else see what I'm missing here? Because the backlight supply is 3 volts and the supply voltage is 3 volts. Where's this VLCD? It's only mentioned in 2 places, and it doesn't explain what that means. Here's the PCB footprint with the outline that you got to avoid. And I like it has these pins that hold it in, which will be good if it's getting swung around a lot. Okay. I think this is the perfect little display. We just got to select or figure out what that voltage for the LCD is. Or where it goes in at. Is there multiple versions, maybe? I mean, because I like that it comes in different colors, too. We can get it in red, blue, or white. Where is it? Here. You get a white. No. Here. There's a white, a blue, or a red version. You know, so you could, like, get one that kind of matches the color of what you're kind of doing. What's the difference in this fourth one? Transflective, transflective, transmissive. Oh, I bet this is a slightly nicer screen or something. Oh, all of these have a black kind of pixel thing, and this one is a white. I actually kind of like the white better. All right. Let me just check this one datasheet real quick. Maybe this one's a little different. No, yeah, same things. 3-volt VDD, 6-volt VLCD. I don't understand. What is going on there? I like this one a lot. I'm gonna pick it, but I'll have to follow up on it. I'll have to ask somebody I know about this just to see what they say. All right, so this gives us our screen. Oh, I'm so excited we're picking out parts. Actually, this goes on the PCBA, so we drop this here, actually, because it mounts directly. I can't wait when we price all this out and find out the lightsaber is going to be like $2,000 each, you know? All right, I like that a lot better. Oh, you know what? There's something else I need to look at too. First, let me mark this as done. Good. All right, we still need to pick buttons. And we need for power on as well. Yeah. And I found one that I liked that I wanted to use for the power switch. Chargeable's good. USB-C port. I think we said this is good as well. All right, we'll do buttons, and then I guess we got to do sound effects, and then we can look at these other ones. Okay. Push button. This one. Or similar to this one. These rugged metal RGB push buttons. That you can turn them to basically any color. I really, 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 really want to use one of these. I have no idea how the RGB component works. Oh, okay, there's more connectors there than I thought. It's pretty big though, so we'll have to take that into. Well, actually, this looks smaller though. Oh, this is it with it like pulled out, like this piece pulled out from the inside. Or there's smaller versions here. They have bigger ones too. They have 22 millimeters. I thought they had 19s as well. Huh. Hold on. They have their own lightsaber kit thing. Oh, it's a YouTube video on how to do it. That's kind of cool. We can do better. I guess we could 3D print it and then... wow, this one uses NeoPixels as well. And their big battery pack. And their charging board. A lot of the things that I was thinking of using. That's really cool, actually. So it shows us that we're on the right track, that this is doable, and that we're making good progress here. Okay. Why is this so zoomed in? I could have sworn they had a 19mm one. 19.5 millimeters. So that's not that big either. Yep, I like this one a lot. This is going to be our power button. 3350. Oh, the 19mm is out of stock. Which one's that? 3425. This is a pretty sizable one. So okay, so it has to use PWM on the RGB pins. That'll be a little tricky. But I want to make that work. Let me check out the datasheet for this one. 38.2 millimeters. It's close. It's going to be tight in there, like in terms of not getting too far to the end. But I think it works. So do we use the 19 or the 6? I guess the 16. I like the bigger button just because it's a little more satisfying. But spacing gets a lot more complicated. And I do want to try and do a thinner handle, which a big button would look kind of weird on anyway. So yeah, I think we go with the smaller one. If we mock it up and it looks weird in CAD, then we can always switch it out. All right, I guess I gotta find this on a website, on Mouser or something. Three 3350. Here it is. Perfect. In stock it is. $10.95. Works for me. Okay. I need to where's the bill of materials? I need assembly. That's PCBA assembly. This one. Here's where it goes. All right. Well, I think we made a lot of good progress tonight. So many cool things. Different stuff worked out. I like it. We still have a long way to go. But so many parts are picked out now. Like our power button's good, so now we just need to use our input buttons and our speaker. And then the motor. And then we need to figure out the light features on the hilt somehow. I'm not totally sure about that one yet. So we'll see. But yeah. I think we made really good progress. And I can't wait to keep working on this more. I can't wait till we pick out all the parts finally so I can actually start designing it. And kind of the contrast to last time, I think we'll start in CAD first this time, like designing the 3D model, because that is going to determine a lot about like how our circuit board fits in there, the sizing of it, and everything. So I think we have to start off by designing in CAD, and then we just need to be flexible and work between them because we're going to have to tinker with things on both sides a lot until we get it right. In other news, I got some more parts for the MIDI controller. I've got the USB-C converters and the rubber feet, and yeah, that's coming along. So the circuit boards have shipped. They're done being made. They're in the mail. They should be here. I don't know, however long it takes FedEx to bring something from China to the U.S. And yeah, we just go from there. So next time, hopefully, we will be actually building the MIDI controller itself, not doing this project. So sorry if that's kind of disappointing. We'll be taking a break, but it'll be cool because it'll be a lot of like actual like building physically, soldering, and screws and putting things together. So that'll be really cool. I need to still get a Dremel or something and figure out how I'm gonna do that because I think if I'm sitting here cutting ABS plastic in the dining room, uh, my wife will not be happy. So I'll have to figure out exactly how I'm going to do that. But yeah, I'll keep you all updated on Twitter and everything, and we will go from there. All right. I will see you all later. Bye.